In this video, I'm going to solve a question about the hypothesis testing for two proportions. A simple random sample of the front seat occupants involved in car crashes is obtained. So among 2,823 occupants not wearing the seat belts, 31 were killed, and then among 7,765 occupants wearing the seat belts, only 16 were killed. We want to use the 0.05 significant level to test the claim that the seat belts are effective in reducing fatalities. Okay, so in this case, we are looking at the proportion, the ratio, and there are two proportions. So let we write here. I call this is proportion, the population 1, and this is the population number 2. Number 1 is the one that are not wearing the seat belts. Okay, so not wearing the seat belt. And then the second population is the one that wearing the seat belt. Wearing the seat belt. Alright. Okay, so we see right here for not wearing, we have the sample N1, 2A, 2, 3, and then 31 were killed, that is X1. 31. And then for the other population, N2, we have 7,765 not wearing the seat belts, and then only 16 were killed. So this is what's given for you. And then the alpha, the level of significance is 0.05. Now, we need to find what is the p hat 1 and p hat 2. So I can find p hat 1, right? This is the proportion of the first populations. So I take x1 divided by n1. So 31 divided by 2a 2 3, and then I also find the proportion p hat 2, which is x2 divided by n2, and that is 16 divided by 7,765. Okay, and now it is time for us to check the requirements. So make sure that the sample proportions are from the two simple random sample, which is what the problem gave you, and make sure that the sample are independent. That means the sample values selected from one population are not related to the other population. This is also true. And then we need to make sure that there are at least 5 successes and 5 failures. So make sure that you check the inequality N1 p hat 1 bigger than or equal to 5, and N2 p hat 2 bigger than or equal to 5. And you also need to check N1 q hat 1. Q hat 1 is just 1 minus p hat 1, the complement of p1. And then also N2 q2 hat bigger than 5. So they are all satisfied for the requirement checking. Okay, now we can use the p-value method. But before that, we need to determine what is the null hypothesis and what is the alternative hypothesis. So now I'm looking to get what is H0 and what is H1. Now we always assume that the value of P1 is equal to the value of P2 originally for the null hypothesis. Again, P1 is the population proportion for not wearing the seat belts, and P2 is the population proportion for the one that wearing the seat belt. And then H1 is the claim. We are looking to test the claim that the seat belts are effective in reducing fatalities. Reducing the fatalities mean the ratio of the sample that wearing the seatbelt is less than the one that is not wearing. So P2 is the population proportion of the one that wearing the seatbelt. If this is effective, then this ratio is small. That means we have a smaller rate of the people that die from the car accidents. So P2 should be less than P1 because P1 is the population proportion for the one that is not wearing the seatbelt. And we are looking for the effectiveness. We say that, okay, the seatbelt is very effective. That means the one that wearing the seatbelt, which is P2, should be less than the one that don't wear the seatbelt. Because if you wear the seatbelt, your death rate is smaller than the one that do not. So we are looking to test for this claim. And because this is bigger than P2, or the arrow is pointing to the right, this should be the right tail. The right tail case. And now we need to find the test statistic. So what is the test statistic in this case? That is the next step. Okay, test statistic. The test statistic is defined as Z0 and then P hat 1 minus P hat 2 divided by the square root of P hat 1 minus P hat, and then 1 over N1 plus 1 over N2. So we need to find what is the P hat value. P hat value, this is the poor estimate. The poor estimate. The poor estimate. And the poor estimate of the proportion P, this is the best estimate of the common proportion. And this is obtained by pulling both the samples into one big sample. And this is found by getting the x1 value plus x2 value divided by n1 plus n2 value. x1 plus x2, n1 plus n2. We got everything here. 31 plus x2, 16 divided by n1 plus n2. That is the poor estimate. And then after you have everything, you have P hat 1, you have P hat 2, and then you have P hat and 1 and 2. You have everything. If you plug in the calculators correctly, you should be able to get 6.11 for the test statistic. 6.11. And then now we have to use the to find the p-value. We need to draw the normal curve. So this is Z0 and Z0 is 6.11. So let me just put it right here. Z0 6.11, and we are looking for the claim is a right tail. So that should be all the value to the right. This is the p-value. The p-value is the area to the right here. And I can find the p-value. It's very simple. I can just using the normal, the p-value. It's just the normal CDF function on my TI-84. And then the first, we are going from here. So we go from 6.11, the lower limit. We go all the way to the right. So I just put a very large number to the right. And the mean is 0. The standard deviation is 1. This is the syntax that I'm plugging in the TI-84. So to use that function, I go to second var to get me distribution, and I go to normal CDF. The lower bound I want to stack from 6.11, and I want to go all the way to the right, so I put a very large value. The mean is 0, standard deviation is 1, and I hit enter, and that will give me like 5.00 to 10 to the negative 10. 5.000. This is extremely small. You can think of this one as like super small number or 0. Now, because this one is less than alpha. Alpha is what? Alpha is 0.05. So if the p-value is less than alpha, we then reject the null hypothesis. Reject the null hypothesis. If we reject the null hypothesis, that means we have enough evidence to support the claim saying that the seatbelts are effective. So there is sufficient evidence to support the claim that the fatality rate is higher for those that not wearing the seatbelts, and that is the conclusion. So there's sufficient evidence to support the claim that the fatality rate is higher than those not wearing the seatbelts. We support the claim. Okay, part B. This is part A. We test the claim using a hypothesis test, especially using the p-value methods. This is part A. Part B. Test the claim by constructing an appropriate confidence interval. So let's do part B over here. Now recall that we assume that the null hypothesis H0 is when P1 equal P2. If we make the assumptions, this means when I subtract P2 on both sides, I get a 0. So this means we can construct a confidence interval estimate of the difference between the two proportions P1 minus P2. Now, if the confidence interval does not include 0, because the difference between them is 0. So if the confidence interval does not include 0, we have the evidence suggesting that P1 and P2 have different values. If they have similar value, then their difference should be 0. If they have different values, then when they subtract each other, we don't get a 0. So only when they are equal, then the difference is 0. Okay, so the confidence interval uses a standard deviation based on estimated values of the population proportion, whereas a hypothesis test uses a standard deviation based on the assumption that the two proportions are equal. Okay, so now we can perform the constructing the confidence interval, and we know that we have the level of 1 minus alpha 100% of confidence interval for the P1 minus P2, and we are given the lower bound and the upper bound as below. So this is the lower bound formula, which is P hat minus E, margin of error, and that is the same thing as P1 minus P2, P hat 1 minus P hat 2, minus Z alpha over 2, the critical value, and then take the square root of P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2. So that is the lower bound. And we do the same thing for the upper bound. The upper bound, we just change the minus to the plus, so P hat plus the margin of error, and that is the same thing as P1 minus P2 hat, and then plus instead of minus, and then the other things they are the same. So P1 and then 1 minus P1 over N1, and then plus P2 1 minus P2 hat over N2. And now we are ready to plug in the values for these variables in the two equations here. The first thing is we have to find the critical number, the critical values for the z distributions. So given the fact that alpha is 0.05, the from this problem 0.05 significant level, and recall that this is the right tail test. Okay, this is the right tail, so we only draw the right tail right here, and we give 0.05 because this is the right tail, so you do not divide by 2. Okay, we give the whole value of alpha equals 0.05, only the right tails. And to find the critical value right here, we simply use the inverse norm function from a TI-84 and make sure we use the left area of that location. Because this is 0.05 for the area, so whatever the left should be 1 minus 0.05. So I just go to my TI-84 and I use my second distributions, and I go to inverse norm, make sure that the area is the area on the left side of that critical value. So 1 minus 0.05, the mean is 0, standard deviation is also always 1, and I get 1.6645. So that is my critical value here. So I go ahead and I plug in the lower bound and the upper bound. So my lower bound is, if after I plug in everything, I should be able to get, if I plug in this equation right here, I should be able to get 0.00559. And if I do the same thing, I should get the upper bound to be 0.0123. So this is the lower bound, this is the upper bound, and the difference between the two proportions P1 and P2 is between these two lower and upper limits. And we can make the conclusion that because the confidence interval limits do not include 0, right? This is 0.00 something up to 0.00 something to the right side, so it is above the 0. So it does not include the 0 as inside the limit. It appears that the two fatality rates are not equal, because if they are equal, when you subtract them, they should have 0, or 0 should be inside the lower and the upper limit, but now 0 is outside. And because the confidence interval limits include only the positive values, it appears that the fatality rate is higher for those not wearing the seatbelt. That means P1 is bigger than P2, so that when you subtract them, you get a positive value. And that's why the fatality rate is higher for those not wearing the seatbelts. So this is a 90% confidence interval for this example. This is one tail, the right tail, so we focus on the right tail only. We do not divide alpha by 2. So this portion right here is 5%, and because this is symmetrical, there's another 5% here. So the confidence interval should be 90%. 90%, 5 and 5 give me 100. And part C. What is the question? Part C is asking you, what do the results suggest about the effectiveness of the seatbelts? Well, it is very clear that the results suggest that the use of the seatbelts is associated with fatality rates lower than those associated with not using the seatbelts. And that is our conclusion above as well.